Hello, I am Frédéric Bour. I work at Terides, an OCaml shop, and I am also a PhD student at INRIA's Cambium team. Welcome to this presentation. Today I will tell you about Nottui and LWD, two libraries for making user interfaces in OCaml. The first library is Nottui. Its purpose is to easily output structured interface to a terminal and to process user inputs. We are targeting developers UI, something above printf debugging, for more interactive but similar use case. It's not meant for mainstream use. The second one is LWD, or lightweight document. It's a form of incremental computations, a bit like Excel. If you look at this graph, input values propagate to compute new results. When an input changes, we discard invalid results and restart the computation. And here is an example of what can be done with these libraries. CT is a terminal client to the continuous integration service of OCaml Labs. In this demo, you can see the list of repositories being monitored. For each repository, a list of branches, and for each branch, a list of jobs to run. When a job is selected, you have access to the execution log. Everything is asynchronous. All the content is streamed from the network, and the UI updates accordingly. It demonstrates mouse and keyboard navigation, scrolling, word wrapping, and so on. Now let's take a deeper look at the first library, Nottui. To understand what it is about, we first need to know about Nottui. It's an OCaml library for declaring terminals, according to its author, David Caloper-Mercignac. It solves two problems: programming terminal images that are represented as pure values, that's the declarative part. A terminal image, it's a matrix or grid of styled characters. And then it takes care of the low-level work involved in managing TTY without messing the console and while rendering images and processing keyboard and mouse input. But how to build these terminal images? First, you build primitive images, generally a character or a string, with some styling attributes. Here are two OCaml lines to make a fancy hello world. Then we can compose existing images into richer ones. We can concatenate, superpose, crop, pad, etc. You can see two ways to compose our fancy hello world. Because everything is made of immutable values and composed with pure functions, that's a very pleasant way to work in a functional setting. However, these images are not really suitable for user interfaces. We have identified two main limitations. First, they are fixed size. They embed no layout information. But at runtime, the size of the terminal is not fixed and known in advance, and sometimes the size of the content to display changes too. So we would like more flexibility here. And second, it is really only about display. It has only visual informations. But to react to input events, a user interface generally has behaviors that follow the structure of the image. So we would like to attach more meaning than just visual to images. We solve the first problem with a layout domain-specific language, or DSL. It is loosely inspired from TeX. The idea is that there are fixed size objects that have some space requirements and stretchable ones that can adjust to the space available. To implement that, we extend the notion of dimension to be a pair of integers. The fixed part is the same as Nottui images size. It's a reserved number of columns or rows. But the stretch part is a factor that we use to determine how to share the rest of the space. Let's lay out manually a simple sentence as an example. Hello and world, separated by stretchable spaces of different strength. We start from the total space available, say 20 columns. We subtract all the fixed parts, so that's 5 characters for hello and 5 for world. So we have 10 remaining columns. We have to split the stretchable objects over these 10 columns. For that, we sum the factors. The total strength is 2 plus 2 plus 1 equals 5. So we give each stretchable a share of the space split in 5. 4 white spaces for the ones with strength 2, and 2 white spaces for the other one with strength 1. So here is our final hello world. Let's look at the properties of this DSL. First, the composition is very simple to compute. To concatenate two objects, we can just do pointwise addition on fixed and stretched parts. Hello plus stretch 1 results in a dimension with the fixed part being 5 and the stretched part being 1. And second, decomposing a solution is as simple. Given the final dimension and say a physical space of size 8, we know we can give 5 columns to the fixed part and the 3 remaining columns to the stretchable part. Finally, the concatenation operator is associative, which is both very natural for the user and nice for performance. Let's look at the benefits of this DSL. To summarize, it is simple, efficient, and straightforward to implement. It is simple and yet it solves common problems. It can represent text alignments, left, center, right. It can represent tables, and etc. Then it is efficient, because every basic operation is O1, and it fits well within an incremental setting because it can be rebalanced. And finally, the implementation is very simple too. We just have to use functional tools, smart constructors for creating specifications, and direct recursion for decomposing a solution. Now we tackle the second problem with Nottui Lwd, attaching rich behaviors to images. We look at event dispatch. When displayed this dialog box, users already have a lot of expectations. There is a notion of focus. OK is the current active widget. We can move the focus with keyboard and mouse. We can also type text in the input field and move the text cursor with the mouse. We can trigger a button either with the mouse or with the return key. But as we said, the structural information that enable this are lost in an image. So we extend Nottui Lwd with constructors to attach these new behaviors to existing images. For instance, here you can see how to react to mouse input. One can attach a callback that can filter mouse events over an existing UI object. And we have similar definitions for taking care of focus, of measuring, etc. To summarize, Nottui Lwd is Nottui Lwd extended with layout, event dispatch, and context probing. But we have no way to animate things, how to update the content after an event triggered. So this is still only static images. But that's what LWD is for, making things interactive. To understand how we got there, we will take a step back and think about Nottui Lwd as a syntax. Making live documents is not a new problem. HTML has been there before. In Nottui Lwd, we have combinators to describe a document the same way HTML has tags and attributes. To make things interactive, the DOM was derived from HTML syntax. It is a mechanical translation. We take every information from the syntax and represent it by a mutable object. And when the object changes, the browser re-renders as if the original HTML document was changed. The pros of this mechanical approach is regularity in the interface. If you know the syntax, it's easy to find what to change at runtime to get the result you want. The cons of making everything mutable is that the DOM becomes a battlefield where scripts are competing for changing stuff. So we took another route for making things updatable. We propose to use a type transformation. If UI is a type of a document, then UI lwd.t is the type of a changing document, the one that can be updated. To build these values, these changing values, we start from mutable variables with the var type. If we look at just these 3 functions, it's exactly like an ML reference. But we have a 4th function. Rather than sampling the current value of the variable, it gives a changing value, something of type lwd.t. This one will be updated if the variable is mutated with set. With it, we can observe both the current value of the variable and also all the future changes. The rest of a lightweight document is built by composing simpler documents. It actually forms an applicative functor, so functional programmers will be at ease with document building. The pure function returns a constant, a changing value that never changes. Map transforms a single value that will change when its input change. And map2 transforms a pair of values, returning a changing value that changes whenever one of its input changes. And at last, it also forms a monad. I won't enter the details, but this is important for dynamic documents, where not only values can change, but also the shape of the document. For instance, think of a list that is dynamically populated. Elements are added, swapped, or removed. Now that we have a rich notion of changing value, we need a way to observe them and act based on their value at the current time. And this is achieved with routes. First, you create a route by observing a changing value. To get the actual value at the current time, you sample the route. And when you are done with it, you can release it. The evaluation strategy is quite naive. We re-evaluate the parts of the computation for which at least one variable changed since last time. And this is only about dependencies, not about values. So you could even use a unit LWD var to just be notified about an event. Now an example. Our goal will be to count the number of clicks on an element, on a visual element. We will start with a simple syntax for the sake of the example. The text constructor displays some text on screen. The link constructor attaches a callback to an existing document, for instance when it is clicked, and the cat constructor concatenates two documents. So first, we display some information and manage the counter state with a function to increment it. Then we construct the link by displaying the current state and attaching the callback. And the final document is a concatenation of the information label and the link. With an appropriate renderer, it will display as follows. If we click it, the counter is incremented, but there is no way to update the document. It's a pure value. To remedy this, we first switch the state from being a reference to being a variable. Then we lift the rest of the document to depend on the counter state. Now, if we click the increment link, the counter gets incremented. Now we will compare LWD to other libraries. The first one is Jane Street Incremental, which is an implementation of self-adjusting computations. The main difference is that LWD is only about dependencies and not about values. So we never need to check for equality or to memorize. LWD is about observing and reacting to updates, while incremental is about speeding up the evaluation of a pure function. So the change should not be observable from an incremental computation. This is fine to do in LWD. In practice, LWD is really just a subset of SAC, but with a simpler evaluation strategy which makes it easier to mix with effectful code. It also has a smaller overhead, but in exchange it does a lot more recomputations and has no notion of cutoff. It is fine for building documents, where the spine of the computation is often just applying constructor, but not for general purpose computations. Another point of comparison is React.js, a JavaScript library for making user interfaces. But React.js is really an abstraction of the DOM, while LWD aims to replace the DOM. So React.js could be used as a front end when it is convenient on top of LWD. A last point of comparison is Svelte.js, a metaprogramming tool for JavaScript that aims to overcome the limitations of the UI frameworks. I didn't know about it, so thanks to the reviewers for pointing it out. It is indeed very similar to LWD. It has the same intention, but a very different implementation because of the different ecosystem. I am looking forward to their progress as it is a very inspiring project. Nottui and LWD have a few unusual features that I thought were interesting to point out. First, as we have seen in the CT demo, the integration with LWT is transparent. You can have asynchronous UI running without problems. The document construction is still synchronous, but all changes happen concurrently, driven by LWT. The only thing to change is how the UI is run. The default is a synchronous main loop, and an asynchronous main loop is provided by an optional library. Then we have two data structures for dealing with incremental collections, a mutable and an immutable one. With them, you represent an ordered collection of items, which can be observed using MapReduce combinators. This abstraction meshes very well with incremental updates. Then we ported and made incremental a pretty printing library. Since we intend to use Nottui for PLT problems, it is quite handy. The pretty printing engine we provide derives from Wadler prettier combinators, but rather than just being about text, any UI element can be put in pretty printed documents, and it supports the full layout DSL. The only drawback for OCaml users is that it is quite different from the built-in pretty printer format. Maybe we could emulate that in the future. Here you can see a demo pretty printing some ML terms. Pretty printing adjusts to the space available. And then we have a second demo which is about text alignment. So here you have the word wrap text pretty printed with left, right, justified and center alignments. We were quite lucky to have early adopters, so we will take a look at some applications that are already using Nottui and LWD. The first one is tooling for Better Boy, a Game Boy emulator written in OCaml. Emulating hardware requires accuracy and can exhibit subtle bugs. Custom toolings helps a lot. So a debugging shell was made for Better Boy and it is driven by Nottui and LWD. Here you can see the video memory being inspected, and in this slide you can see the code around the program counter displayed in an interactive disassembler. Our other user is iMandra, an automated theorem prover. The internal state can grow quite complex in automated theorem proving, and in this terminal you can see Nottui being used to inspect it. In front, it's a GraphViz window showing the proof term selected by Nottui. Nottui and LWD are two pure OCaml libraries for making user interfaces. So far, they compose quite well and have been shown to solve real-world problems. In the future, there are a few areas that we would like to improve. First, we need to polish the current implementation. Resource management, the deterministic acquisition and release of external resources, in particular, needs some rework. And we would like to have a common set of widgets provided out of the box for consistency and ease of use. Then, targeting the web is important to us. LWD seems particularly suitable as a safe interface on top of the DOM, and we would like to provide a uniform experience when developing native and web user interfaces. And third, we need to think about bidirectional data bindings. Everything we have seen so far propagate updates one way, from input model to the view. It's very convenient for visualization, but not so much for editing documents. There, each widget has its own ad hoc logic for doing state update. Providing a common abstraction for thinking about this flow will be important to enable new kind of applications. That's all about this presentation. Many thanks to you for attending it, and a special thanks to our early adopters, Simon Cruernes and Enguerrand de Corne. I am here if you have any questions.